Most FPGA ICs have built-in JTAG state machine with boundary scan outhoused. This concept of JTAG and boundary scan are not very much connected to SDRs. At this moment these will ultimately need to be incorporated into SDR chips. Most RF designers are not the least bit familiar with these concepts. This presentation is an overview of the concepts. Maybe later on I will come up with a JTAG boundary scan presentation which will try to handle the needs of RF circuits, which will also incorporate RF testing. Boundary scan tutorial. Since its introduction as an industry standard in 1990, boundary scan, also known as JTAG, has enjoyed growing popularity for board-level manufacturing test applications. Boundary scan has rapidly become the technology of choice for building reliable high-technology electronic products with a high degree of testability. Due to the low cost and IC-level access capabilities of boundary scan, its use has expanded beyond traditional board test applications into product design and service. This article provides a brief overview of the boundary scan architecture and the new technology trends that make using boundary scan essential for dramatically reducing development and production costs, speeding test development through automation, and improving product quality because of increased fault coverage. The article also describes the various uses of boundary scan and the tools available today for supporting boundary scan technology. Free design for testability analysis. What is boundary scan? Overview of the boundary scan architecture and the new technology trends that make using boundary scan essential for dramatically reducing development and production costs. The article also describes the various uses of boundary scan and the tools available today for supporting boundary scan technology. Boundary scan applications. Read how boundary scan technology can be applied to the whole product life cycle, including product design, prototype debugging, production, and field service. This means the cost of the boundary scan tools can be amortized over the entire product life cycle, not just the production phase. What is boundary scan? Boundary scan, as defined by the IEEE STD 1149.1 standard, is an integrated method for testing interconnects on printed circuit boards (PCBs) that are implemented at the integrated circuit IC level. The inability to test highly complex and dense printed circuit boards using traditional in-circuit testers and bed-of-nail fixtures was already evident in the mid-80s. Due to physical space constraints and loss of physical access to fine-pitched components and BGA devices, fixture and cost increased dramatically while fixture reliability decreased at the same time. A brief history of boundary scan. In the 1980s, the Joint Test Action Group JTAG developed a specification for boundary scan testing that was standardized in 1990 as the IEEE STD 1149.1 to 1990. In 1993, a new revision to the IEEE STD 1149.1 standard was introduced, titled 1149.1a, and it contained many clarifications, corrections, and enhancements. In 1994, the supplement containing the description of the boundary scan description language (BSDL) was added to the standard. Since that time, this standard has been adopted by major electronics companies all over the world. Applications are found in high-volume, high-end consumer products, telecommunication products, defense systems, computers, peripherals, and avionics. In fact, due to its economic advantages, some smaller companies that cannot afford expensive in-circuit testers are using boundary scan. The boundary scan test architecture provides a means to test interconnects between integrated circuits on a board without using physical test probes. It adds a boundary scan cell that includes a multiplexer and latches to each pin on the device. Boundary scan cells in a device can capture data from pin or logic signals, or force data onto pins. Captured data is serially shifted out and externally compared to the expected results. Forced test data is serially shifted into the boundary scan cells. All of this is controlled from a serial data path called the scan path or scan chain. Figure 1 depicts the main elements of a boundary scan cell. By allowing direct access to nets, boundary scan eliminates the need for a large number of test vectors, which are normally needed to properly initialize sequential logic. Tens or hundreds of vectors may do the job that had previously required thousands of vectors. Potential benefits realized from the use of boundary scan are shorter test times, higher test coverage, increased diagnostic capability, and lower capital equipment cost. Typical boundary scan cell. The principles of interconnect test using boundary scan are illustrated in Figure 2. Figure 2 depicts two boundary scan compliant devices, U1 and U2, which are connected with 4 nets. U1 includes 4 outputs that are driving the 4 inputs of U2 with various values. In this case, we assume that the circuit includes 2 faults, a short between nets 2 and 3, and an open on net 4. We will also assume that a short between 2 nets behaves as a wired and an open is sensed as logic 1. To detect and isolate the above defects, the tester is shifting into the U1 boundaries can register the patterns shown in figure 2 and applying these patterns to the inputs of U2. The inputs values of U2 boundaries can register are shifted out and compared to the expected results. In this case, the results marked in red on nets 2, 3, and 4 do not match the expected values and, therefore, the tester detects the faults on nets 2, 3, and 4. Boundaries can tool vendors provide various types of stimulus and sophisticated algorithms, not only to detect the failing nets, but also to isolate the faults to specific nets, devices, and pins. Interconnect test example boundaries can applications. While it is obvious that boundaries can based testing can be used in the production phase of a product, new developments and applications of the IEEE 1149.1 standard have enabled the use of boundary scan in many other product life cycle phases. Specifically, boundary scan technology is now applied to product design, prototype debugging and field service as depicted in Figure 3. This means the cost of the boundary scan tools can be amortized over the entire product life cycle, not just the production phase. Product life cycle support Figure 3. Product life cycle support. To facilitate this product life cycle concept, boundary scan tool vendors such as Coralys offer an integrated family of software and hardware solutions for all phases of a product's life cycle. All of these products are compatible with each other, thus protecting the user's investment. By applying boundary scan for product development, the ongoing marketing drive for reduced product size, such as portable phones and digital cameras, higher functional integration, faster clock rates, and shorter product life cycle with dramatically faster time to market has created new technology trends. These trends include increased device complexity, fine-pitched components, such as surface mount technology, SMT systems in package SIPs, multi-chip modules, MCMs, ball grid arrays, BGAs, increased IC pin count, and smaller PCB traces. These technology advances, in turn, create problems in PCB development. Many boards include components that are assembled on both sides of the board. Most of the through holes and traces are buried and inaccessible. Loss of physical access to fine-pitched components, such as SMTs and BGAs, makes it difficult to probe the pins and distinguish between manufacturing and design problems. Often a prototype board is hurriedly built by a small assembly shop with lower quality control as compared to a production house. The prototype generally will include more assembly defects than a production unit. When the prototype arrives, a test fixture for the IC is not available and, therefore, manufacturing defects cannot be easily detected and isolated. Small size products do not have test points, making it difficult or impossible to probe suspected nodes. Many complex programmable logic devices, CPLEs and flash memory devices in PGA packages are not socketed and are soldered directly to the board. Every time a new processor or a different flash device is selected, the engineer has to learn from scratch how to program the flash memory. When a design includes CPLEs from different vendors, the engineer must use different in-circuit programmers to program the CPLEs. Boundary scan technology is the only cost-effective solution that can deal with the above problems. In recent years, the number of devices that include boundary scan has grown dramatically. Almost every new microprocessor that is being introduced includes boundary scan circuitry for testing and in-circuit emulation. Most of the CPLE and field programmable array FPGA manufacturers, such as Altera, Lattice and Xilinx, to mention a few, have incorporated boundary scan logic into their components, including additional circuitry that uses the boundary scan for wire interface to program their devices in system. As the acceptance of boundary scan as the main technology for interconnect testing and in-system programming ISP has increased, the various boundary scan test and ISP tools have matured as well. The increased number of boundary scan components and mature boundary scan tools, as well as other factors that will be described later, provide engineers with the following benefits. Easy to implement design for testability DFD rules. A list of basic DFD rules.